Now it's time to prove the divergence theorem. Omega is piecewise smooth. Omega is bounded closed, and which piecewise smooth boundary. And f is a C1 vector valued function over omega. Our conclusion is that the divergence of the integral of f equal the boundary surface integral. Okay, so we will prove this result. So we consider the special case f only has the last component non-zero. Consider this case first. And omega is n-type. Omega is n-type. What's n-type? N-type means that omega is ut. U is taken from an n-1 dimensional region. For region in Rn-1, omega can be expressed in this way. T belongs to the interval determined by phi minus u, phi plus u. Here phi minus and phi plus are functions defined over u, C1 function defined over u, and also phi minus not greater than phi plus. Okay, such domain are called n-type of n-type. So we have a picture here. This is Rn-1. So this is u. Then this is the graph of phi plus. This is the graph of phi minus. The graph of phi plus always above the graph of phi minus. Then the domain bounded by this. This domain is n-type. This is the omega. Okay. So such domain we have already encountered when we studied the Fubini theorem. Okay. Of course, we can also have other type of domain, I-type. I-type, that is, the i's coordinate is bounded by the graph of two functions of the other variables. So our n-type domain is that the n's coordinate of the point, the n's coordinate of the point in the domain, that is our t. T is bounded by two functions of the other variables. Okay, so this is n-type. Similarly, I-type domain is that the i's coordinate of the point in the domain is bounded by two functions of the other variables. Okay, I will not write this out. It is boring. Okay. Now, for such omega, we know that the boundary of this omega, consists of three parts. Here, sigma positive or negative are graph of the phi plus and phi minus. And the sigma 0 is the vertical part of the boundary. Sigma 0, this part is sigma 0. So this part is sigma plus, this part is sigma minus. Okay, the boundary of omega consisting of these three parts. And on the sigma 0, the nu, the normal vector, on sigma 0, the normal vector is horizontal. The first n minus 1 component, I don't care, but the last component is 0. Okay, therefore, the inner product of f and nu is 0. Because f has only all the components of f are 0 except the last one. But the last component of nu is 0. So their inner product obviously is 0. Okay, so this is the first observation. And then we also have on the other two parts, we know that nu is positive or negative minus 1 n plus 1 norm of n. Okay, this we just studied. We just studied this case for the graph of a function. We know that for the graph of a function, n is here. N is of this form. You have minus 1 n plus 1 and also has the last component to be 1. Okay, so that is the n components. That is n, sorry. n is minus 1 n plus 1. Because in front of this, we have minus 1 n plus 1. And we have a 1 inside. So this means that the nth component of this normal vector is minus 1 n plus 1. But we want to make it to be 1. Therefore, we multiply minus 1 n plus 1 again. That is 1. So that is here. That is why we write minus 1 n plus 1 n here. This make the last component of this vector to be 1. And then we divide it by the norm, making this unit vector. And since the last component of this is positive, we see that when sigma positive, the normal vector nu point upward. Point upward means that the last component is positive, so we choose positive sign. Okay, well, on the lower boundary, sigma minus, the outward normal vector point downward, so the last component is negative, so we need to take the negative sign. Okay, so we get this result. So this is the normal vector at all parts of the boundary. We have three parts. Sigma 0, the normal vector is horizontal. This is easy. And for sigma positive and sigma negative, we need to go to our previous result here. We explained just now, and so that we can study this slightly a little carefully. You will see that our nu is really given by this, and this can be written by positive or negative 1 norm of n. Then something here, in fact, that is the gradient of, maybe I will write this out. That is the gradient of phi plus negative. The last component is 1. The important thing is the last component. But the other the other component is actually the gradient of phi plus and phi minus, but we don't need this. So from this expression, we see that the inner product of f and nu is just positive or negative. Okay? Because although we have the gradient of phi here, but the first n minus 1 coordinate of capital F is 0. Therefore, making inner product, we only have Fn multiplying 1. So that is why we have Fn here. Okay, and the positive and negative sign and the norm of n keep unchanged. Okay, so this is the inner product of F and the unit outward normal vector on all part of the surface or the boundary of omega has been determined. Okay, now we are ready to get our divergence theorem. So the boundary of omega f and nu. So this is sigma positive plus sigma negative. Sigma 0 is 0 because when sigma 0, the inner product of f and nu is 0, therefore the integral is 0. So we only have the integral over sigma plus and sigma minus. And when sigma plus and sigma minus, you have f nu is fn over the norm of n. So so this is u f n u c plus u. Maybe I don't go too fast. You see, the sigma f nu is the f nu replacing the xu here, and then the norm of the corresponding normal vector. But f nu, but this part, by our previous study, this part is fn divided by the norm of n. Okay, so here we will have u fn, the norm of n, and then this is also the norm of n du. Therefore, we only have u fn du. Okay, so by this observation, for sigma plus and minus, all these are true. Okay, so but for sigma plus and minus, this also has a positive and negative sign. So we take a positive sign for sigma plus and a negative sign for sigma minus. So at this step we have u fn u phi u then du minus u fn phi plus u phi minus u du. And this can be written by u du phi plus u phi minus u. Okay, maybe I don't write xn, I write the derivative with respect to the last coordinate. Okay, Newton-Leibniz formula. this definite integral equal capital Fn at the value of capital Fn when t equal to phi plus u minus the value of Fn at the value at t equal to phi minus u. Okay, so we obtained this result. Okay, so this red board equal Fn u phi plus u minus Fn u phi minus u. So the previous step equal this one, but this is precisely this result is precisely the integral of over omega. This is precisely the integral of this partial derivative over the domain omega. But because our capital F is 0 Fn, so the partial derivative is precisely the divergence of Fn. Divergence of F. So the last step equal divergence of F. So for our special case, that is for vector field F of this form and the domain of n type, our result is true. The divergence theorem is proved. Now we consider the slightly general case. We say that omega is prime domain if omega is of I type. For all I. This notation I invented. This notation is invented by myself. This means 1 n. This means I use this notation to denote all the positive integers not greater than n. Okay, so if omega is I type for all n, all I not greater than n, such omega is called prime domain. So we want to consider prime domain. So we suppose omega is prime domain. Then for general F, omega is restricted, it should be prime, but our F can now be general. Previously we require F has only one non-zero components. Of course, our proof here is we prove that the last component, only the last component is not zero. In a similar manner, you can prove the result for other non-zero, other component not zero. For example, only the first component not zero, the divergence theorem true. Only the second component not zero, the divergence theorem also true. Okay, but now we study the general F. Maybe none of these components is zero. So, but we require the domain to be prime. Okay, then the surface integral of F is equal because such F can be written by the sum of simple vector field. Here this is the i's location. Okay, then this will be denoted by Fi. So the general F can be written by the sum of all the Fi. super index fi means the ith component of f, but lower index of fi, here fi is 0, 0, fi 0, 0. The super index case, this fi is a real valued function. It is the ith component, but the fi here is a vector valued function. Different. The meaning is different. You should not confuse this. Okay. Now, for this, our f nu d sigma can be written by the sum of maybe I should fi nu d sigma. Of course, this equal fi nu, and you can compute, switch the order of integration and the summation. Now, for this integral, because the fi here has only one non-zero components, and the domain, the omega, is of I type, because for all I, omega is I type. Okay, so by our previous argument, we know that for this, the divergence theorem is true. Therefore, we get